Today we're going to be learning about cube roots of unity and geometry of complex numbers. So, we learned in the last video about the introduction to complex numbers. We learned imaginary constants and uh, representations of complex numbers. As you know, you can represent a complex number in this form, where a and b belong to real numbers. So we learned an introduction to algebra in the last video. Today we're going to end it off by learning about the cube roots of unity, and then we're going to start geometry of complex numbers. So, what is the cube root of unity? A cube root of unity basically means cube roots of 1. So, if you have an equation x cubed equals 1, then we know that x equals 1 to the power of 1 over 3. And this is just 1. But since it's a cubic equation, it should have 3 roots. Where are the other 2? We're going to solve for the other 2 roots of this equation. So, if we subtract 1 from both sides, you get x cubed minus 1 equals 0. And 1 is the same as 1 cubed. So, we're going to write it here. X cubed minus 1 cubed equals 0. And we know an identity, a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So we're going to apply that identity here, giving us x minus 1 times x squared plus x plus 1 equals 0, which means both of these factors are equal to 0. When we keep x minus 1 equals 0, we get x equals 1. And then when we keep x squared plus x plus 1 equals 0, we get x. So to solve this equation, you can see that b squared minus 4ac has no real roots because, this equation has no real roots because the discriminant is less than 0. We learned in the last video that if the discriminant is less than 0, a quadratic has imaginary roots. So, how do we find the imaginary roots of this equation? We can use the quadratic formula. We know that the quadratic formula is minus b plus or minus the square root of b squared minus 4ac over 2a. So, what is minus b here? Minus b is negative 1 plus or minus b squared minus 4ac, which is 4 times 1 times 1 over 2 times 1. So simplifying this, we get minus 1 plus or minus the square root of negative 3 over 2. And we know that the square root of a negative number is just that square root times I, because let's say you have the square root of negative a. Write it like this. The square root of negative a is equal to the square root of negative 1 times the square root of a. So this is just the square root of a times I. So we're going to apply this here. And this is going to give us minus 1 plus or minus I times the square root of 3 over 2. So as you can see, when we solve this equation, x cubed equals 1, we had an equation, x cubed equals 1, and when we solved it, we got 3 different roots. One of them was 1. Another one of them was minus 1 plus I times the square root of 3 over 2. And another one of them was I minus 1 minus I times the square root of 3 over 2. And these are the cube roots of unity. These are your cube roots of unity. Why are they called the cube roots of unity? Because they are cube roots of 1. So they are known as the cube roots of unity. Now there are some names for these cube roots of unity. So minus 1 plus I times the square root of 3 over 2 is called omega. And this is a Greek symbol, like this, omega. And minus 1 minus I times the square root of 3 over 2 is actually equal to omega squared. So, from this relation, you can see that if you square this whole quantity right here, you're going to get this. What can we inquire from this? So we know that omega and omega squared both satisfy this equation, which means omega squared plus omega plus 1 is equal to 0. And omega squared plus omega equals negative 1. And if you substitute, let's just keep this in a little box, or not. So if you substitute omega squared, you get omega squared whole squared plus omega squared plus 1 equals 0. And from this, you get omega to the power of 4 plus omega squared equals negative 1. So you need to remember these two formulas. Now we're going to talk about powers of omega, or the cube roots of unity. So we know that omega to the power of 1 is just omega. Let me write that down clearly. Omega to the power of 1 is omega. And omega squared is still omega squared. And what you're going to observe is omega to the power of 3 is 1. And why is that? Because omega was a cube root of unity, which means if you cube the cube root of unity, you're going to get unity, or 1. And what is omega to the power of 4? Omega to the power of 4 is just omega cubed times omega, which is 1 times omega, giving you omega. And omega to the power of 5 equals omega cubed times omega squared, giving you 1 times omega squared, which is just omega squared. So I think you can observe a pattern here. And if you calculate omega to the power of 6, you get omega cubed times omega cubed, which is 1 times 1, and that's 1. So what you observe here is a pattern is repeating. Omega, and then omega squared, and then 1. And then it goes back to omega, and then omega squared, and then 1, and it just keeps repeating. So what can you inquire from this? Feel free to pause the video and think of a relation between omega's powers. So omega to the power of 3 times n, omega to the power of 3 times n equals 1, where n belongs to any integer. And what we can see is that omega to the power of 3n plus 1 equals omega. And omega to the power of 3n plus 2 equals omega squared. And omega to the power of 3n plus 3 is equal to 1. And omega to the power of 3n is also equal to 1. So these are your powers of omega and the cube roots of unity. And we're going to go over a small topic before we dive into geometry of complex numbers. So we're going to learn how to find roots of a quadratic where the coefficients belong to complex numbers. Like, for example, if I had x squared minus I times x plus 2I equals 0. Let's say this was your um, quadratic. Now, how do you solve this? It's very simple. We just use the quadratic formula. Minus b would be I plus or minus the square root of b squared, which is negative I squared, which is um negative 1, minus 4ac, which is 8I, over 2 times a, which is 1. So you get I plus or minus the square root of negative 1 minus 8I over 2. And that's just how you solve for complex roots of an equation which has complex coefficients. Now we're going to go over geometry of complex numbers. What is geometry of complex numbers? So we know what a Cartesian or coordinate plane is. We graph it like this, and we know this is the x-axis and this is the y-axis. But what if I told you there was another plane for complex or imaginary numbers? And in that plane, this is the real axis. Use a different color. Real axis. And this is your imaginary axis. So this is your polar plane or argand plane, complex plane, whatever you want to call it. But for the sake of this video, I'm going to call it the complex plane. Now, in this complex plane, we graph points. We can graph different complex numbers. Like if I gave you z equals 2 minus 3I. This is your real coordinate. I told you this was real part of z equals 2. And the complex part or imaginary part is equal to negative 3. So let's graph that here. So the real part of 2, or the real part of this complex number is 2. And then from here, we go negative 3. 1, 2, 3. Which gets us, so if we graph this out, this point is right here. This is your complex number, which is z. So use a different one. This is z. And as you can see, it makes some, if we draw a line from here, from the origin to this point right here, this distance that's covered is actually the modulus or absolute value of z. And how do we prove that? I think I've proved this in the last video, that it is the square root of a squared plus b squared. And then you get this hypotenuse side, which is your modulus. So, and you can see that here, it makes some angle with the x-axis. And in this case, it would be something like this. And we're going to call this angle theta. And this angle right here, theta, is known as the argument of a complex number, denoted by arg of z. So this is a basic understanding of the complex plane, arguments of complex numbers, and plotting them on a line. Now we're going to talk more about arguments of complex numbers. So let's say you have, and actually there is a formula for the argument of a complex number. Argument of a complex number is given by argument of z is given by tan inverse or arctan of the imaginary part of z over the real part of z. Now, how do we solve this? Let's say I give you, and an argument is just the angle that that point makes with the x-axis. So we're just finding the angle with this. Let's plot a graph and I'll show you an example. Let's say your argument here, let's say the point was somewhere here. And this point was z, where z equals 3 plus 5i. And they told us to find this angle right here. This angle. So let's find this angle. So how do we find this angle? First, what we need to do is find the imaginary part of z. So from this, we can say that the imaginary part of z equals 5, and the real part of z equals 3. So this angle would be theta equals, or arguments of z equals tan inverse or arctan of 5 over 3. And if you use a calculator, you will get some angle in radians or degrees. It doesn't really matter now. So this would be your angle. And if you had a better option, I would use something like z. Let me give you a better question. So I'm going to plot this graph, and I'm going to ask you to find the arguments of a complex number, where the imaginary part is 6 and the real part is 6. So your complex number is z equals 6 plus 6i. So let's say it was somewhere around here. And I want you to find this angle. So what is the real part of this complex number? The real part of z is equal to 6, and the imaginary part of z is also equal to 6. So you can see here that if you do tan inverse of the imaginary part of z over the real part of z, you get tan inverse 6 over 6, which is just tan inverse of 1. So for this, we need to know when. So how do you solve an inverse trig function? I'm going to explain that clearly since I haven't done that yet. So when you have an inverse trig function, tan inverse of 1, you're going to let it equal some theta or something, some angle or variable. You could say y, you could say x, and you're going to take tan of x on both sides. And these are going to cancel out because they are inverse functions. And you're going to see that tan of theta equals 1. And they're asking you for which theta is tan equal to 1. You could think and tell me in the comments, and that is going to be your argument of z. Now we're going to learn about polar coordinates of a complex number and the Euler coordinates. So we've only seen one representation of complex numbers so far, and that's z equals a plus bi. Now what if I told you there were more? Like z equals r times cosine of theta plus I times the sine of theta. Now, what even is this? So if we graph this out in trig functions, you're going to learn that x coordinates is cosine of theta and the y coordinate is sine of theta. In polar coordinates, you're going to learn that this is going to be r cosine of theta and r sine of theta in a real axis. So in a real axis, this is what the polar coordinates of a point would be. But see, here we're learning about complex numbers, and if sine of theta is the y coordinate, it has to be multiplied by I. And why is that? Why does it have to be multiplied by I? Because we know that it's across the imaginary axis. Only if it's across the imaginary axis will it be a y coordinate. So it has to be multiplied by I. So this is your polar form of a complex number, and I'm going to show you how to plot graphs using this form. So what is your polar form? Z equals r times cosine of theta plus I times sine of theta. Let me write that down clearly. I times sine of theta. So let's graph this out. What is r? R is your distance from that point. This would be your r. And theta is the angle which it makes with this x-axis. And then you can graph your point. So let's say I said, if I gave you theta, let me draw that clearly. If I gave you theta equals 30 degrees, and the modulus of z equals the square root of 3 over 2, how would you plot the point? Where would you plot the point? You have a few seconds. I'm going to give you a few seconds. And if you still don't get the answer, you can pause the video. So let's solve this. Theta equals 30 degrees. And the modulus of our complex number is equal to the square root of 3 over 2. And they want us to find this complex number and graph it. How do we do that? Let's plot the complex number first. Now, they said this angle would be 30 degrees. So let's draw something that's accurate. Say this is 30 degrees. Well, not exactly, but approximately. And this is your angle theta. So they gave us theta equals 30 degrees. So we'll just write 30 degrees. And the modulus of z is r. I told you this distance from the point is the modulus of your complex number. So this would be 5, right? In the question, that's 5. Now they're asking us to find the point. And to find this point, you know your formula or your general polar coordinate form for a complex number, which is r times cosine of theta plus I sine of theta. And this is going to be 5 times cosine of 30 degrees plus I times the sine of 30 degrees. Now you're just going to leave it here. If they ask you to convert it into polar coordinates, or they give you polar coordinates, or they give you the angle and the modulus, and they ask you to find the original complex number, you could just leave it here, but I'm going to simplify this and turn it into a plus bi form. So this would be 5 times cosine of 30 is the square root of 3 over 2, plus I times sine of 30 is 1 over 2. So this would be, so I gave it, my bad. So actually, here, your modulus is the square root of 3 over 2. And if we solve this, we're going to get the square root of 3 over 2 times cosine of 30 is the square root of 3 over 2 plus I times 1 over 2, which is just I over 2. And if we solve this, this is the square root of 3 over 2 whole squared plus the square root of 3i over 4. And this is going to give us 3 over 4 plus the square root of 3i over 4. And this is your complex number, where the real part is 3 over 4. The real part of z equals 3 over 4. And the imaginary part of z is the square root of 3 over 4. And sometimes they'll give you a complex number and they'll ask you to find the polar coordinates. How do they do that? So, let's say this is your real axis and this is your imaginary axis. And they ask you, let's say they give you a complex number. The square root. So they give you r, or they give you the complex number z equals the square root of 3 over 2 plus 3i, let's say. And they give you the angle. The angle, let's say, is 30 degrees. Or this would be more appropriate, yeah. So the angle is 30 degrees. And they ask us to find it in polar coordinates. So, if you observe this complex number properly, we can take the square root of 3 common. And this would be 1 over 2 plus the square root of 3 times I. And you could consider this your r. So then r equals the square root of 3, and theta equals 30 degrees. Let's plot that. So this is your line, and your point z, and your angle is 30 degrees, and your modulus is the square root of 3. Now, let's plot it in polar coordinates. We know that z equals r times the cosine of theta plus I times the sine of theta. And this is going to be the square root of 3 and cosine of 30 plus I times the sine of 30. And this is a basic introduction to your polar coordinates. Before we wrap up this video, we're just going to go over Euler's coordinates, where there is one more form of complex numbers. So far we've learned to z equals a plus bi, z equals r times the cosine of theta plus I times the sine of theta. And our third form is z equals e to the power of I times theta. How would this work? So let's say they give you theta equals pi over 2. Then your complex number would be z equals e times I to the power of pi over 2. So this is just a general introduction to Euler's um identity for complex numbers. And there is one more identity, which is known as Euler's identity. And this is e to the power of I theta plus 1 equals, this is I pi, plus 1 equals 0, which means e to the power of I pi equals -1. So this was just a clear finish to the algebra of complex numbers with the cube roots of unity. And then we went over geometry and rotation of complex numbers, arguments of complex numbers, and basic inverse trigonometric functions, I would say. So in the next video, we're going to talk about sets and relations or functions or trigonometric ratios and identities. I'll see you in the next